professor of philosophy at Shaanxi University. Shan is a philosopher of physics, mostly working on quantum mechanics. He is a founder and managing editor of the International Journal of Quantum Foundation. He has published extensively on quantum mechanics, on issues around quantum mechanics, including his book, The Meaning of the Wave Function in Search of the Ontology of Quantum Mechanics. He has also edited various volumes on quantum mechanics and on issues surrounding quantum mechanics, including recently consciousness and quantum mechanics. Today, Shan will be talking about what does quantum mechanics tell us about reality. 2022 as a mind and philosophy of physics. And last but not least, he is a visiting fellow at the center this semester. And we've been really enjoying having you with us this semester. Thanks, floor is yours.
Yes, thank you very much. And thank you all for coming. I'm very glad that my child Richie has also come here. And he studies classics at Yale and will graduate this year. I'm so proud of him. Okay, today's talk is about the meaning of quantum mechanics. But let me first tell you a story. When I attended a conference in Copenhagen 10 years ago, a Danish physicist told me that he knew the meaning of my Chinese name, Gao San. That was a great surprise to me. In Chinese, Gao means high, San means mountain. He called me high mountain. But later, he told me that he married a Chinese wife. So in the end, that was not so surprising when the reason is not. Okay. Okay, quantum mechanics is a difficult subject to understand. Its meaning has been debated by Albert Einstein and Niels Bohr. Bohr once said, you can't have understood quantum mechanics if you are not shocked when you first learn it. Richard Feynman even claimed that nobody understands quantum mechanics. The reason, according to Roger Penrose, is that quantum mechanics makes no sense. In this talk, I will try to make sense of quantum mechanics and find what the theory tells us about reality. My talk is composed of 4 parts. First, I will use a double-slit experiment to illustrate what the mystery of quantum mechanics is. Then I will present my idea to use a particular measurement to find the ontology of quantum mechanics. In the third part, I will introduce my interpretation of the wave function. Finally, I will argue that this new interpretation may also have solved the measurement problem, and the result will be a time division multiverse. Let's first see the double-slit experiment for electrons, which, according to Feynman, contains the only mystery of quantum mechanics. It is well known that classical mechanics can explain the result of this experiment, namely the inference pattern formed by detecting a large number of electrons one by one on the screen. By contrast, the predictions of quantum mechanics using Schrödinger equation and Born's rule agree well with the result of the experiment. Then, what is the mystery of quantum mechanics? The mystery lies in understanding the startling and counterintuitive result. What do they imply for the nature of reality? An electron is represented by a wave function, but it's still unclear what physical state this mathematical function represents. Exactly what is an electron? How on earth does a single electron pass through 2 slits? In order to know what an electron is, an effective way is to measure it. Indeed, we can measure the mass and the charge of an electron and know what values they assume. But it seems impossible to measure the wave function of a single electron. Here is a simple example. Consider an electron being in a superposition or even superposition of the ground states in two boxes. We can use the test particles to detect which box the electron is. A conventional projective measurement will yield one random result. The test particles will be detected either in position 1 or in position 2 on the screen. This result only indicates that after the measurement, the electrons will be found in one of the boxes, either in box 1 or in box 2. But it does not tell us where the electron is before the measurement. The wave function of the electron will be changed by the experiment, and it effectively collapses to one of the wave functions in the boxes after the measurement. So in order to know where the electron is before the measurement, we need a measurement that does not change the wave function of the electron. Is this possible? The answer is surprisingly yes. Such measurements have been discovered by Aharonov, Weidmann, and another in 1993. The basic idea is to protect the measured system, such as the measured electron, in a certain way, so that its wave function does not change during a usual projective measurement. Then the measurement result will be the expectation value of the measure observable in the measured state. By a series of predictive measurements, one can also measure the whole wave function. This is a surprising result for many people familiar with quantum mechanics. As we will say, this may be the key to find what an electron really is. Please note that such predictive measurements have been realized in recent years for the photon polarization. Consider again the above example. For predictive measurement, the test particles wave packet will arrive at the position 0 on the screen without any deviation. So this result is indeed surprising. As I noted before, we may maybe use this result to find the ontology of quantum mechanics. Here is a more general case. It is a predictive measurement of the charge distribution of electrons. The electron is a general superposition in the ground state in two boxes. For this predictive measurement, in order to have a causal explanation for the deviation of the test particle, one must assume that there is a fraction of the total charge of the electrons in each boxes. In other words, the charge of an electron is distributed in space, and the charge density in each position is equal to its total charge multiplied by the modular square of the wave function of the electron there. This reminds us Schrödinger's charge density hypothesis proposed in 1926. presumably because people thought the charge distribution can't be directly measured, and it also lacks a consistent physical explanation. This hypothesis has been largely ignored. I think this is a great pity. It can be seen that there are two possible origins of the charge distribution. One is that the charge distribution is real, which means that it exists throughout space at the same time, like a continuous field. The other is that the charge distribution is effective. In this case, there is only a discrete particle with the total charge of the system in one position and every instant. And the time average of its motion forms the effective charge distribution. Then which one is true? Here is my analysis. First, two continuous charge distribution can form an entangled state for a many-body system. So this suggests that the charge distribution is not like a continuous field. Next, if the charge distribution is real, then it is arguable that there will exist electrostatic self-interaction of the distribution. But this not only violates the superposition principle of quantum mechanics, but also contradicts experimental observation. So it seems that the second possibility is favored. This means that at every instant, there is only a localized particle with the total mass and the charge of the electron, and the time average of its motion forms the effective mass and the charge distribution. In other words, the electrons are indeed particles. In a previous paper, I have given a more detailed argument against the field ontology and favoring the particle ontology. The next question is, how do these particles move? Consider again electrons being in a superposition of the ground state into boxes. If the electron being a particle moves continuously with a maximum speed, then it can only form a charge distribution during a minimum finite time interval. But according to quantum mechanics, the charge distribution is required to exist during an arbitrarily short time interval around a given instant. Moreover, a particle moving continuously can move from one box to the other box to form the charge distribution in both boxes. So it seems that the motion of the particles can be continuous, but be discontinuous. Besides, in order to form the right charge distribution, the probability density that the particle appears in each position should be equal to the modulus squared of its wave function there at every instant. Since quantum mechanics provides no further information about the position of the particle at each instant, the motion of the discontinuous motion of the particles must be also random according to the theory. Then we have arrived at a particle analogical interpretation of the wave function. It is that the wave function in quantum mechanics represent the state or random discontinuous motion of particles, or RDMP. This is quite like the case of classical mechanics, where the trajectory functions represent the continuous motion of particles. Take the electron in a hydrogen atom as an example. The random discontinuous motion of the particles will form a mass and charge cloud in space. In mathematics, the density and the flux density of the cloud can constitute the wave function. So then the ontology of quantum mechanics will be particles in our three-dimensional space. These particles undergo random discontinuous motion, and the wave function can be regarded as a propensity property of the particles that determines their motion. Here we also have a clear picture of motion for two entangled electrons. The wave function that describes their motion will be naturally defined in the six-dimensional configuration space. So this new interpretation of the wave function have been proposed and analyzed in very great detail in my book, The Meaning of the Wave Function. The idea of random discontinuous motion of particles first came to my mind when I was a postgraduate at Chinese Academy of Sciences more than 30 years ago. You can download the book draft from the Philosophy of Science archive at the University of Pittsburgh. So, did anyone anticipate this strange picture of motion in the history of quantum foundations? Maybe John Bell did. In his famous article against the measurement Bell said, the wave function gives not the density of the star, but gives rather the density of the probability. Probability of what? Exactly, not of the electron being there, but of the electron being found there, if its position is measured. Why this aversion to being and insistence on finding? Moreover, in 1981, Bell also proposed the bomb theory without trajectories. He said, instantaneous classical configuration acts are supposed to exist and to be distributed in a comparison class of possible world with probability the size square, but no pairing of configuration at different times. What would be effected by the existence of trajectories is supposed. The question is RDMP bomb theory without trajectories? I think the answer is no. Bomb theory without trajectories, also called it Bell's aberrant question mark theory, is Bell's interpretation of the aberrant theory aiming to remove the picture of many worlds from the theory. Recently, I have argued that this theory as a one-world theory contradicts quantum mechanics and experiment. Moreover, a proper understanding of RDMP will lead to a picture of many worlds, and this many world theory solves the measurement problems and agrees with experiment. Concretely speaking, the theory explains the Born rule for the original measure M for every instant. M will obtain only one definite result at every instant after measurement. And the probability of M obtaining this result is equal to the Born probability. but still all results occur during a time interval after measurement. Different results are obtained by different descendants of M at different instants, and they coexist in a time division multiplexing way during an arbitrarily short time interval around a given instant after the measurement. Here, words are defined as usual by decoherence, as explained by David in his great book, The Emergent Multiverse. But these words do not coexist at the same time, according to RDMP, rather than exist in a time division multiplexing way in different time subflows. For example, in the Schrödinger's cat thought experiment, there are two worlds or two sides of worlds, a live cat world and a dead cat world. They coexist in different time subflows. It is also worth noting that the many-world theory and the single-world theory will give different predictions about the small probability result. The former predicts that there will be descendants who obtain small probability result with certainty, while the later predicts that the small probability result will almost never occur. So here is a summary on the RDMP interpretation of quantum mechanics. First, the ontology is particles undergoing random discontinuous motion in three-dimensional space. Primitive ontology is not postulated but derived here. Second, the wave function is a propensity property of these particles. This may explain entanglement and why the wave function is defined in a high-dimensional configuration space. Third, the random discontinuous motion of particles forms a time division multiverse. This have solved the measurement problem and where the Boyle's rule has a natural origin. Okay, thank you.
Yeah, we have a lot of time for questions. Let's take a 2-minute break and then let's reconvene for questions.